We're going to be talking about InfraGuide today, which is focused IR welding for clean plastic parts. Our agenda is we're going to talk about how InfraGuide works, why InfraGuide is better than other IR welding technologies, and why manufacturers who have written off IR welding, like we're not going to do any more IR welding, but now they are deciding, you know what, we can do IR welding as long as we do InfraGuide. We'll also look at what materials work best with InfraGuide technology. And then, of course, we want to get to your questions about InfraGuide, and not just at the end. We will have a time at the end for questions, but ask your questions throughout. Quickly, this is a brief kind of highlight view of like who Xtol is. We have innovative technology for manufacturing plastic parts. We build custom automation, and we have engineering services like 3D printing. Our applications lab, we help customers come up with manufacturing concepts for their product and their application. And what else? Service and support, all kinds of things. So we're really here to help improve the way that plastic products are made. So first, what is InfraGuide? InfraGuide is a welding process that uses focused, and that's key. It's focused IR energy to heat and weld plastic parts. So the tooling includes several independent IR emitters and reflective geometries that are used to direct and focus that energy onto the weld rib where you want to weld your parts. It's kind of, in a way, it's similar to like hot plate welding or other technologies where there's something that comes in between the two components that are being welded. It heats those components up, and then that tooling gets out of the way, and then we bring the parts together to weld. So let's take a look at a video here of InfraGuide in action. So the part is brought close to the tooling, and you can see the IR light is turning on. Actually, the light that you can see is visible light. IR light is invisible. So there's a little bit of overlap in the wavelengths that are coming out of the emitters. And then there, the parts are brought together, and you can see the beautiful flash oozing out of the weld joint. We're going to see another video as well. Should I play it again?
I thought it was a great video.
Okay, well, let's play it again. In case somebody didn't catch it, or maybe it was buffering too slowly on your end. You also notice that the light is flickering. That's intentional. So we can flicker the light in order to effectively reduce the rate at which it is heating the part. There are certain times where you don't want to heat it as fast as you possibly could. All right, so pretty simple. First you heat the parts, and you can see there in that graphical representation. I think I can actually zoom in. No, I can't.
Oh, they couldn't hear you over the video.
Oh, shoot. Okay. Well, this is great because I'll talk through the process right here. Thank you, Rita. So first, what you saw in that video is the tools came forward, and those infrared emitters were turning on, and those are heating that weld surface. You also might have noticed the flickering that happened during the video. That is intentional. So that allows us to reduce the rate of heating on the plastic parts, because the surface of the plastic is what's absorbing that infrared energy, and we're heating that surface and then allowing it to conduct deeper into the weld rib for a greater heat affected zone. And some materials and colors absorb that energy faster than others. And so if you were to heat them super fast, then they would burn or smoke or something like that, and you want to slow it down a little bit. I got a question here. Can't see the question.
The question is, can you heat different zones to different temperatures on the same part?
Yes, we can absolutely heat different zones to different temperatures. So because we have independent bulb emitters inside of the InfraGuide tool, we can independently program every single bulb. So you can basically say, this zone I want more heat, and this zone we want less heat. Usually when we're doing that, the goal is to get even energy distribution along the entire weld. So if for example, some area, you have the same settings across the board, and there's a certain part geometry that maybe is just taking a little bit longer to heat up, or whatever the reason might be. That area, you can say, I want to heat longer, or I want to have more intense energy. And so it's very tunable.
One thing to note as well about the InfraGuide kind of tunability is we don't set the bulbs to a certain temperature. So you're not getting the bulbs or the material to kind of a certain temperature, like above the melting point. It is programmed by time. So that's kind of how it's different from some of the other IR technologies in the industry as well.
All right, and then of course the other parts of the graphic of the process are fairly simple. Once the energy is into the part and heated up, the tool is removed, and then the parts are brought together for weld. All right, so here's another video, and I won't talk over this one because you guys won't be able to hear me apparently. Okay, so there you might have noticed that a couple of things. One, it's a much smaller weld. And so that shows some of the versatility in the sizes of InfraGuide tools and the different applications that you can use it for, which we'll get into a little bit later. But also the actual equipment that was used was very different from the first video. And so there's just a whole wide range of like different equipment sizes and styles that we can use this technology in. What would happen when there is moisture in the parts? Great question. So moisture in plastic is never a great thing with welding in general. And so when you have a lot of moisture inside of your part, you're probably going to see a lot more off-gassing. And so it's generally a good idea to, if you can get your parts to be drier, better. But it's not like the end of the world if your parts have some moisture in them.
We've also seen that moisture in the parts can cause voids in the weld if you do have a really excessive amount of moisture. If you heat that moisture up and it creates a little tiny bubble in the weld rib, so there's potential for leak paths to be generated or exposed. But yeah, drying parts resolves that issue typically.
Yeah. Some other questions here. What is the max size of the part to be welded, and why is the process so loud? So, okay, the max size. Practically, we haven't hit the limit yet. So we've done some applications where the part is quite large, maybe 2 feet long or so. And what that means is you have a lot of bulbs in there, and that means you have to power those bulbs. I'm going to go to the next slide so it's not just a blank screen for everybody. So you have to kind of balance like how many power supplies are used and the size of the electrical cabinet that would be required before you really hit the limit. But yeah, we've done tools where the number of bulbs are spaced typically about 1 inch to 1.5 inches apart.
Yes.
And we've had over 100 bulbs inside of a tool. So you can do fairly large parts, and yeah, we'll get into more of that as well. Why is the process so loud? So that's a great question. There is cooling air passing through the module while it's running. And that is because we want to keep the bulbs from getting too hot. We also want to keep positive air pressure inside of the InfraGuide tooling so that the reflective surfaces don't get coated in the off gas or any smoke that you might see. And that way, if the reflective surfaces stay cleaner, the cleaning cycle, the amount of times you have to clean the modules is extended greatly. And the side benefit of that, maybe it's not a side benefit, maybe it's a primary benefit, is because we're evacuating any off-gassing from the parts, there's no flare-ups that you see. There's no fire from this, which if you're familiar with other infrared welding technologies, you often see flames inside of your tool because you have a very hot emitter next to off-gas vapors, and they ignite. Another question here. The video images in Jason's window appear normal, but the other slides on the presentation appear pixelated. Does anyone else see there's a way of correcting that? Could be a buffering issue on your end. All right, so other IR welding technologies. I'm curious to know which you have used. There's kind of three main types. Quartz IR, which you can tell there has longer tube style bulbs. Sometimes they're straight, sometimes they're contoured to match the part. Metal foil IR, where you have kind of a metal foil, kind of a wire or something like a toaster wire. Some people refer to it as, but it's placed into a machined channel inside of like a ceramic tool. And then of course, InfraGuide. So I'm curious to know, like, which ones are you guys familiar with? Let us know in the chat, like, have you used any of these? Which ones have you used? Because there's kind of pros and cons to every single one of them. Quartz IR. So there's a few things to know about quartz IR. You might experience uneven energy distribution. So the bulb, if you have this tube that's whatever, a few inches long, typically what we see is the middle portions of that bulb are outputting the most infrared energy, and the ends of the bulb aren't outputting as much. And so what that means for your part is you might get a hotter area in the middle and a colder area on the end. And when you try to weld those, you reduce the strength of the part because you don't have even heating along it. You also have limited control. You have one bulb that's going, one or multiple bulbs, but not every inch along the part. And so you're really limited when you try to correct for that uneven energy distribution. You have fewer control zones that you can adjust to try to get to even energy distribution. You also, there's two ways to do this. You can have a tube that matches the contour of your part, or you can have a bank of these. So, a whole rectangle of all these tubes of infrared emitters. And then you have a machined plate that has a hole wherever you want the energy to go. And that works marginally well. You do get the energy to the weld rib where you want it, but there's also some stray infrared energy that kind of goes to some of the other areas of the part where you might not want it. There's also the fire risk that I mentioned, so you get the off-gassing from the material, and it's close to a hot bulb, and you do sometimes see some flares or some flames during your weld. Usually it's not burning any plants down, but people don't generally like that in your manufacturing plant. Is, oh, there's flames inside the welder.
People don't like fire.
Yeah. And then with a long bulb like that, especially a contoured bulb, they can be very expensive to replace. So when they burn out and you have to replace them, they're an expensive cost. Or if you accidentally break one, they can be expensive to replace. Thanks, Jerry. I see that you've done quartz, wire, foil, infrastake, non-contact top plate. Yes, non-contact top plate welding is another way to do it, and we'll kind of get into that in just a minute. Metal foil IR is also characterized by somewhat uneven energy distribution. So you have this foil that goes along the weld rib as anywhere that you want heat to go, and you're applying electricity to that foil to make it heat up, and it's not uniform along the entirety of the part. You have limited control. Wherever that thing is machined, that's where the energy is going to be focused, and if it's not in the right place, you got to like machine your tool to get it to be where you want it to go. And then of course the same fire risk as before. So that kind of leads to some of the benefits of InfraGuide. It's focused and efficient. So rather than trying to mask off where the energy can go, we're just taking all of the energy and focusing it right on the weld rib, and it's not focused anywhere else, so it's not getting absorbed and heating up other areas of the part. It's got uniform energy. Like we've mentioned a couple of times now, you can tune every single bulb independently. You can adjust the rate of heating. You can adjust the amount of time that the lamp is on. And that's really all you need to control the rate at which your parts are heating up. There's no flare-ups because we're using positive pressure to make sure that the gases are evacuated away from the weld, and so there's nothing to ignite. And then it's a clean process. And that's true of any infrared welding processes, that it's a clean process. You're not taking plastic and touching it to a hot tool like you are in hot plate welding. And so it's not going to have any sticking or stringing, and it's not like vibration where you end up with some particulate. Oh, Jerry says they make zones for hot foil. That's true. You can have a couple zones of hot foil. Typically, you don't see as much independent control because there's longer zones than you would with InfraGuide, where you have just a small little area that's being welded. Go ahead.
So there are 3 different IR welding technologies like we discussed. So this is kind of at a glance them compared to each other. Obviously, like we had mentioned, there are strengths and weaknesses to each of them, but this is kind of a like bird's eye view. How do they differ? The biggest things here are the strength. The strength of the weld will be stronger with InfraGuide than with than with the other processes. That's because you are directing that IR energy straight into the weld rib. You're not getting any heat washout or anything like that around on other parts. You're not losing any of that energy, and you get a more uniform distributed melt. The next thing to know is material color. You can weld clear materials with InfraGuide, and it's because that IR is so focused it can heat up clear materials. Now, it's not going to be as fast of a process as what welding a black component would be, but we can weld clear, whereas with the other technologies you cannot. Energy uniformity, Jason touched on this one. InfraGuide is tunable, and you can control each individual bulb to get a uniform melt process. Oh, looks like we got a question. Do you have design guidelines for InfraGuide? Weld rib geometry, required clearances, all that good stuff.
So yes, right now it's the design guidelines exist, but we're working on formatting them into a nice pretty little document. So what we've done so far is when people have questions about how to do this, then we work with them one-on-one on their application. But the document for InfraGuide design guidelines will actually be coming out very soon, probably within the next few weeks.
So just to add on to that, if you do have questions about what the design would look like, feel free to send over, screenshots of CAD, the full assembly and whatnot, and we'd be happy to look at it for you, kind of say what areas might be too close to other part geometry, if the weld ribs are too tight together, things like that. We're happy to give tips and recommendations in the meantime while that document's still being generated. Sensitive applications, InfraGuide is safe for heat-sensitive components because you're directing that IR straight into the weld rib. If you've got a PCB right next to it, you don't have to worry about that IR kind of leaching out and damaging that PCB because it's very contained. And then lastly, there's no risk of flare-up with InfraGuide like the other 2 technologies. Is blowing air to evacuate gases cooling the melted plastic at the same time? That's a great question.
So there is some slight cooling effect, and that's actually a good thing. It helps with the rate of heating, and it helps eliminate overheating on the surface of the weld. But it's fairly marginal. The focused energy is able to be so intense that it doesn't like cause you to have a much longer cycle time. If anything, it might help keep your cycle time shorter because we don't have to wait for the parts to heat up. We're actually helping make sure that they're heating evenly.
So we've got 3 different IR welding technologies, and if you're, not new to the plastic welding industry, you know that there's a lot of other different welding technologies out there. So it can be very overwhelming. We've got so many tools in the toolbox, which is great, but still, how do you know which technology is actually going to be best for you? I probably would also be asking the same question. So in this next little bit, we're going to talk through some different kind of example applications, the different welding technologies that would be available, and kind of why you would choose one technology over the other. Like, where do the pros really start to like set one technology over the next? Another good thing to shamelessly plug here is our applications lab. They are incredibly knowledgeable. They weld with these technologies every single day. So they would be happy to review your CAD and your material and your assembly requirements and walk along this process with you. You do not have to decide your welding technology on your own. In fact, we really kind of want to do it with you. Collaboration is always better. So that being said, you don't have to sift through all these welding technologies. We'll do it for you. We'll write a report outlining maybe what 1 to 3 technologies are best suited for your application, what you would have to change in order to make them feasible with that technology, and then also kind of the pros and cons. So we're going to go at a very high level, kind of what that process the applications engineer would go through, just as some examples to kind of get you thinking about different industries that InfraGuide might be applicable for. But again, very generic. We're not going into any crazy specifics here.
Okay, we got 2 questions real quick.
Oh.
So what is the depth of the melt zone? So it's very application dependent. The heat affected zone, it all depends on how quickly the plastic is absorbing the energy and how like intense we're heating it. And so we work on the application. We're tuning the welding process for the application. And so we get it to go as deep as we need for that particular weld. If it's welding and we're getting a hermetic seal, but we're getting weak strength, that typically points to not a deep enough heat affected zone. And so we might slow down the rate of heating and let it heat for a longer amount of time to get that heat further into the part. So there's no real hard and fast like number of how deep it goes. It's all a matter of tuning the application to get it to be a really strong weld, hermetically sealed. The other question that's on here is, how does energy usage compare? And we don't have any data on the comparison of the 3 different technologies and how much energy they use, how much wattage and all of that. I can tell you that InfraGuide uses 100-watt bulbs, and there's air, compressed air going through the module. I would guess that InfraGuide uses less energy, but not a lot less energy, just because we're not having stray energy go every which way. We're focusing the energy on the part, and then it turns off, when it's done heating the part. So that's about the best I can offer for that.
These are great questions. So the biggest driver for when you would take an IR welding technology or InfraGuide out of the welding toolbox is mainly driven by material. So technically you can use IR welding. Oh, do we get another question? No. Okay. Technically we can use IR welding for all thermoplastics. However, if you were welding something, say like a polypro, you probably wouldn't want to use InfraGuide if you didn't have to, because it's more expensive than your contact welding methods like hot plate. So if there was a case where you did need to use InfraGuide for like a polypro, it's probably in an application that has really high glass content. So high glass content in any material is going to start to wear away at any sort of heated tool. So that would require either frequent replacement of that heated tool. That's probably the biggest downside. You'd start to probably see reduced quality in your weld, increased cleaning, maintenance, stuff like that. So that's when you would start to pull out IR technologies. However, we see them most with materials like nylon and PBT. So those materials, if you've ever touched them to something hot, they're sticky, stringy, they leave crud all over the hot tool. Like, it's just gross. So when you're dealing with materials like that, we like to use a non-contact solution. Another application where we'll see the use of InfraGuide is potentially with PC. So PC coming off of a hot tool, you can get angel hair little strings. You can also get bubbling in the weld joint. So we can use the process to kind of eliminate those angel hair strings in our hot plate welders. However, there's not really much you can do about bubbling. So for A-surface components, we'll sometimes use InfraGuide to kind of preserve that and mitigate that bubbling in the weld rib. So we're going to next kind of shift into those different applications where non-contact solutions are used. That being said, we're going to assume that the material is not hot plate welding compatible. Because like I had mentioned, if you are using a material that can be hot plate welded, you're probably not going to start looking at non-contact solutions because of cost. So now that we understand kind of what materials would drive us to start to look at an IR welding technology, it's also important to know what other non-contact processes there are. So like I had mentioned, this is basically the process that our lab will go through when deciding the right technology for your application. They'll look at the material and all the different potential welding processes, and then kind of weed out your assembly criteria and stuff like that to figure out which one would be best. So that requires us to understand high level of what each of the welding processes are. So on the far left here, we've got InfraGuide. We are now experts in how that works because Jason gave us a great description of what goes on in that process. Then we've got vibration welding. It's how it sounds. One part's held stationary, the other part on top vibrates really, really fast, so it's heated with friction. Once that material is molten, and then the parts will become stationary, that material will cool, then you've got your welded assembly. Then we've got hot gas. So that's heated nitrogen being directed at the weld rib. That then heats up the material. Once adequate melt has been reached, the parts will smash together again. Then we've got non-contact hot plate welding, which I think someone had mentioned they've used in the past. This, again, very close to how it sounds. Similar to hot plate, you've got a really hot tool. However, you just don't touch it. Typically, we try to stay about 60 thou away from the hot tool. So you've got a tiny little air gap between the part and the heated tool. That eliminates the sticky, stringy nastiness on the hot plate. Then lastly, we've got direct laser. Now this one might be a little bit newer of a concept, so shoot any questions in the chat if it's not making sense. But basically, you've got the weld profile of both of your parts exposed towards a stationary laser, and then the laser profile will very quickly trace over the profile of both of the parts until an adequate amount of melt is achieved. That's measured with passes. And then once those passes have been complete, the press will rotate and then smash the two components together. So it's another heat and smash method. However, we're using the laser to heat the weld rib as opposed to a bulb or a heated tool. So again, that might be a little bit of a newer one here. So these are kind of at a glance the non-contact processes that we consider when looking at an application. So the different applications where we've seen non-contact be very prevalent. This is not an exhausted list by any means, but we just want to talk through generally these kind of each categories and see where one might be better suited than another technology. So you've got engine air ducts, small engine fuel tanks, batteries, electrical housings, and then medical devices. So another thing I do want to preface is because we're speaking generally, your specific application might cause the pros and cons to shift of each technology a bit. So again, we'd be happy to just look at it with you and talk through it. So for engine air ducts, all of the technologies would probably work for engine air ducts, but just to kind of go through them, the benefits of InfraGuide here are, like Jason mentioned, the individual control of the areas. We see with engine air ducts, they often have some funky curvature to them. So being able to individually control the geometry in certain parts of the part, putting more intensity into them is a huge benefit of InfraGuide. Then you've got vibration welding. This is a process that's typically pretty fast. The downside of vibration welding here is particulate is generated. So you either need something to pull the particulate out of the part and or have a cleaning process post-welding. So it's not that it's not possible, it's just adding that extra cleaning step to your assembly process is not always ideal. Then next we've got hot gas welding. So this is again that heated nitrogen being directed into the part. This will work, however, engine air ducts can get pretty big, and those tools are very expensive, not only just in general, but if any maintenance needs to occur, if those little hot gas emitters get bent or anything, they're difficult to replace. And then non-contact hot plate welding, again, you keep an air gap in between the part and the heated tool. The downside here is these parts with their fun geometry can have part variation. Crazy, I know plastic parts warp. I wouldn't believe it if I haven't seen it myself. But with that warping, if you can't really retain that part mechanically, there's a chance that the part will have kind of a different gap in between the heated tool and the part than in other areas. So you might not get that uniform controlled melt like what we can get with InfraGuide. And then lastly, direct laser welding. The biggest kind of hurdle here is direct laser welding kind of naturally has a size limitation. Now we do have ways around it by stacking optics and sources and stuff like that to be able to get a larger profile. But in general, the 16 by 16 window for welding is kind of the natural limit of the technology. So if you do have to go outside of that window, it starts to add quite a bit of cost pretty quickly. Next, we've got small engine fuel tanks. So again, benefit of InfraGuide here is you get that very precise control of the IR. And then also with small engine fuel tanks, we see that the material color is often like a natural. So with the non-contact InfraGuide method, we can heat that natural or, more transmissive material really well and still efficiently compared to other technologies. You wouldn't want vibration welding because you don't want that particulate inside your fuel tank. That's probably not great for your engine. Hot gas welding, probably not the most cost-effective solution here. Non-contact hot plate welding is an option. Again, the risk comes in with part warping. If you can retain the part well mechanically, you don't want to just rely on vacuum for something like this if you can help it. And then direct laser welding is potentially an option. Again, that size limitation might cause you to have to increase the price more than what your budget is. Batteries. So we found that InfraGuide has been the best suited technology for this industry because you can protect the heat sensitive components around the weld rib from the IR energy. So with vibration welding, you don't really want to shake all the stuff that's inside of a battery. That seems like something bad waiting to happen. I don't quite understand the chemistry, but it sounds like it's going to explode. Yep. Hot gas welding, again, you don't want to blast a bunch of hot gas all over your battery. Non-contact hot plate welding, you need a lot of clearance in between your weld rib and the heat sensitive components inside the assembly to insulate the hot tool. Typically, people don't have the real estate for that. So although it's possible, again, part restrictions typically are what takes non-contact hot plate welding out of the running for that one. And then direct laser welding, the tooling gets complex because you don't want to tip your battery on the side. Size becomes an issue. And then because battery walls are so tall, you often get warping or bowing of the walls. And your laser profile is set to one area. So if that wall is warping outside of your weld profile, then you're not going to get any melt in that area. So you risk the lack of hermetic seal in the assembly. Next, we've got electrical housings. Again, InfraGuide protects from those heat-sensitive components. The IR is going nowhere near those PCB components or anything like that. Vibration welding, again, typically you don't want any sort of particulate getting in there, clogging up whatever's on the inside of this housing. Hot gas welding is expensive and honestly just not the best for something small like this. Non-contact hot plate welding, you're not protecting any of those PCB components from the heat. And then direct laser welding is a potential here. Because the parts are smaller, they typically hold better to a tolerance. Your part walls aren't as tall, so they're not warping. So we've seen great success with direct laser welding in this industry because you typically just have two smaller halves. They're really easy to rotate, or you get the tooling that comes over and then down. So yeah, there's some different customization options there. Lastly, medical devices. So InfraGuide can do clear material. Typically with medical applications, we see a lot of clear. You can also do kind of different materials to each other, maybe some sort of like fabric to a plastic, things like that. You can kind of mix and match the technology with just the material type itself. Vibration welding. I don't want any particulate in my medical devices. That sounds like, I don't know, a clog waiting to happen, and I don't need that in my life. So vibration welding typically with medical devices is a no-go. Hot gas welding, again, expensive. Medical devices typically have a lot of smaller geometry changes, which can just be higher risk of something getting bent, which again is expensive to replace. So non-contact hot plate welding, this is sometimes an option as long as you don't have heat sensitive components, because the non-contact tool can trace some level of part geometry, but we are limited to kind of what angles and contours you can actually accurately heat up. And then lastly, direct laser welding. Again, medical typically holds pretty well to its tolerancing, so we don't have to worry about part walls warping or anything like that.
Right. So we've covered a lot, and now is the time for some additional questions. I wanted to just kind of quickly point out that InfraGuide is just one tool in the toolbox at Xtol. Our goal is to improve the way plastic products are made, and that means we have a whole range of plastic welding and assembly technologies. We offer 3D printing, we offer design consultation and assistance with getting your joints exactly the way they need to be for whatever welding process your application requires. We have prototype and pre-production services where we can help you figure out, is this part going to perform like I want it to, so we can help with your validation processes. We have testing and all kinds of stuff to make sure that the weld is actually good. And then we have custom automation, so we can build lots of different types of equipment, whether it's a standalone piece of equipment or whether it is a fully automated line of processes that doesn't even require a person to touch it. Are there any other questions? Because we would love to try to help you work on your project and make sure that your plastic assembly goes as good as it possibly can. Thank you all for joining us. You have our contact information on the screen. I hope you all have a great rest of your day. If you think of any other questions, we'll send a follow-up email with the video recording and a PDF of the slides, and you can use that and reply to that with whatever other questions that you have. Thanks, everybody.